This diagram represents the circuit designed for binary phase shift keying, BPSK. A 12 volts power supply is provided to the operational amplifier configured in an inverting mode. The output from the operational amplifier is connected to the CD4051 IC, which functions as an 8-channel analog multiplexer or demultiplexer controlled by digital signals. The CD4051 operates with a 5-volt supply voltage. Its inputs include a square wave, the output of the operational amplifier, and a sine wave. The output is obtained from pin 3 of the CD4051 and is connected to a digital storage oscilloscope, DSO, for analysis and breadboard implementation as follows. The hardware setup looks like this, which includes power supply, function generator, and a digital storage oscilloscope to observe the output. Now, let's configure the DSO, power supply and function generator. As shown, the power supply is set to plus 5 volts and minus 5 volts for the multiplexer, and plus 12 volts and minus 12 volts for the operational amplifier. After ensuring all connections are correct, let's observe the output on the DSO. As shown, the phase of the sine wave shifts corresponding to changes in the square wave. This phase shift occurs because the multiplexer toggles between 0 degrees phase output and 180 degrees phase shift output. The switching is controlled by the square wave, which acts as the control signal for the multiplexer. The 180 degrees phase shift is achieved through the inverting amplifier connected to the multiplexer. As a result, the multiplexer operates in 2 states, switching between them based on the square wave input. Now, let's discuss binary frequency shift keying, BFSK. The circuit diagram is shown. Its operation is similar to BPSK, but unlike BPSK, BFSK does not require an operational amplifier since no phase shift is involved. BFSK relies on switching between 2 different frequencies, controlled by the message signal, which is a square waves. As seen, the power supply is set to plus 5 volts and minus 5 volts for the IC. 2 sine wave frequencies are provided as inputs, along with the message signal. The switching between the 2 sine wave signals is determined by the message signal, which controls whether the output corresponds to high frequency or the low frequency. And breadboard implementation as follows.
Let's configure the function generator as shown. 2 function generators are used to provide sine waves at different frequencies. One set to a low frequency of 2 kHz and the other to a high frequency of 5 kHz. A third function generator is used to provide the message signal, which is a square wave with a frequency of 500 Hz. This message signal controls the switching between the 2 sine wave frequencies. After ensuring all connections are correct, let's observe the output on the DSO. As seen, the frequency of the sine wave changes in response to the square wave. The switching between the 2 frequencies occurs based on the state of the message signal. The hardware setup looks like this, which includes a power supply, function generator, CD4051, and a DSO to observe the output. If you enjoyed our video, don't forget to like and share.